Another paper on enhancing sinks of CO2 in soils, and obviously has a lot of chemistry because it's doing mineral applications to enhance soil drawdown, which means I'm going to be brief and not get too much into the chemistry of things. And I'm still having some issues of allergy. So applying minerals to soil to draw down atmospheric carbon dioxide through synergistic organic and inorganic pathways. We'll see what that means. Minerals in soil can sequester atmospheric carbon dioxide through natural organic and inorganic processes. We have already seen how the natural sources can be reduced and natural sinks can be enhanced. We looked at basically land use management, grazing, agroforestry, restoring wetlands, peatlands, and so on and so forth. Here it is much more of a geoengineering approach. Here we consider 3 soil and mineral-based methods for carbon dioxide removal: grinding and spreading of calcium and magnesium-rich silicate rocks for enhanced rock weathering, and subsequent inorganic carbon formation. Secondly, mineral doping of biomass prior to conversion into biochar for enhanced biochar carbon yield and stability. Thirdly, strategic application of minerals to soil to increase soil organic carbon accrual and stability. We argue that there are I just had a cup of coffee, but I'm not awake yet. We argue that there are powerful synergies between these approaches for carbon dioxide removal through organic and inorganic pathways. We find that primary silicates, as contained in basalt, can benefit both enhance weathering and soil organic carbon formation, while phyllosilicates, and other reactive secondary minerals may have positive synergies for biochar and soil organic carbon. Optimizing such synergies may substantially enhance economic and environmental benefits, yet these synergies require accurate quantification, and we already know that increasing soil carbon content has a virtuous cycle of increasing soil moisture retention capacity, other nutrient uptakes, reduced soil erosion, and so on and so forth. So several carbon dioxide removal or CDR methods function by enhancing natural biogeochemical cycles that remove and sequester CO2 from the atmosphere. Minerals play a key role in several of such methods through interactions with carbon in soil, including inorganic carbon, soil organic matter, and plant biomass. These result in CDR, carbon dioxide removal. Here we describe 3 soil-based CDR approaches that use minerals, namely inorganic carbon storage through the application of crushed silicate minerals to soil, what is called as enhanced rock weathering, and mineral doping of biochar to store persistent pyrolyzed organic carbon, and accrual of soil organic carbon through additions of reactive minerals. In brief, these 3 processes occur as follows. During weathering of calcium and magnesium-rich silicate minerals, CO2 is removed from the atmosphere and stored as dissolved inorganic carbon in the Earth's soils, subsurface geological deposits, waterways, and oceans. So there is a pathway for that inorganic carbon to go down deeper and get sequestered in a stable form. This natural process results in about half a gigaton of CO2 drawdown annually. So what is the comparison? We are emitting right now about 30 to 40 gigatons of CO2. Through enhanced rock weathering, i.e. the deliberate crushing and subsequent spreading of silicate dust, between 0.5 and 2 gigatons of additional CO2 could be removed, or 5 to 20% of the CDR needed by 2050. So another way to look at it is, if we want to hit net zero by 2050, how much carbon dioxide removal is needed, and enhanced rock weathering can give us 5 to 20% of that, assuming we have done the life cycle analysis to say this is really going to remove additional CO2. Okay. Secondly, when plant biomass is turned into pyrogenic carbon under high temperatures and low oxygen levels, i.e. during fires, the pyrolyzed material can persist for long time scales in soil we call biochar. This material is termed biochar when it's intentionally produced for the purpose of environmental management. Biochar production has the potential to remove 0.03 to 6.6 gigaton of CO2 per year. That's a large range. During pyrogenic carbon biochar formation, though, minerals can enhance carbon retention and persistence, i.e. biomass with higher mineral contents produce biochar that comprises a greater proportion of organic carbon in persistent fractions. Biomass can be doped intentionally with minerals to enhance this effect, and that's where we look at C. Organic carbon storage in soils, as soil organic matter or SOM can persist over long time scales through interactions with the soil minerals, which limit oxygen and microbial access to this material so it doesn't get respired. SOM is the largest terrestrial carbon pool, so about 1500 gigaton of carbon equivalent, and the most persistent fractions are mineral associated and aggregated organic matter. To increase SOM stock, it's possible to increase organic inputs to soils or to enhance the capacity of soil to retain more persistent forms of SOM. The latter may be achieved via mineral amendments of soils, though this method that has yet to be has yet to be quantitatively assessed in the field. The sentence is a bit awkward. However, the total potential for SOM accrual globally by all land users is estimated at 0.4 to 8.6 gigaton CO2 per year. So you can see that from 0.5 to 2 gigaton amounts to 5 to 20%. So these two methods are much higher than that in the upper end. Let's just quickly look at the reactions. Enhanced rock weathering of calcium and magnesium rich silicate rocks, natural processes weather rocks on geologic time scales, which is very long. They drive long-term variations in atmospheric CO2 levels through Earth's history and remove about 0.5 gigaton of CO2 from the atmosphere per year. Physical weathering causes rocks to be broken apart. During chemical weathering, calcium and magnesium rich silicate rocks react with carbonic acid, so CO2 dissolved in water, ultimately stabilizing the dissolved CO2 in the form of bicarbonate and carbonate. So we see that here. This dissolved inorganic carbon in waters of soils, rivers, oceans, and Earth's crust is stored for periods of up to thousands to millions of years. So that's a very effective sequestration for the time scales we are interested in. So equation 1, 2 CO2 in gaseous form plus 2 H2O gives us 2 H2CO3 aqueous, so carbonic acid with silicate gives us bicarbonate and calcium ions and H2SiO3 in aqueous form. And of course bicarbonate and calcium can interact or react to give us calcium carbonate in solid form, precipitates out, and CO2 back in gaseous form and H2O. So overall you want to make sure that one molecule of CO2 is taken up in the solid CaCO3 form. Some rocks release all the calcium back, all the CO2 back, whereas silicate rocks rich in calcium and magnesium can put away one molecule for the take up. So it's a net sink. So jumping ahead, role of minerals in 3 soil-based carbon dioxide removal methods. A is enhancing carbon retention as inorganic carbon through enhanced rock weathering. So this is the reference scenario. We have vegetation, there is photosynthesis going on, organic carbon into the soils, and you are releasing some of the CO2 during respiration. And in the enhanced rock, so A is when you have enhanced weathering, so you have enhancing carbon retention as inorganic carbon through enhanced rock. So you add minerals and you enhance the weathering, so inorganic carbon gets locked in, eventually through groundwater and other ways makes it into the ocean and gets put away, let's say exported to the bottom and so on with mineral addition. You can do biochar, as we talked about with pyrolysis. You add biochar, already things that we discussed happen. So enhancing stable biochar formation via pyrolysis facilitated by addition of minerals. And C is limiting respiratory CO2 emission by enhanced conversion of plant carbon into persistent soil organic matter. And in panels under 1, reference scenario is outlined. Panels 2, the effect of minerals on the reference scenario is shown. So you have reference scenario here, enhanced inorganic carbon pathway, and here you have pyrolysis, enhanced biochar, so mineral biochar, and enhanced soam, organic matter, and here you have other methods that we talked about with mineral additions to limiting respiratory CO2 emissions. Okay, so reference scenario and enhanced mineral additions for persistent soil organic carbon. And there are synergies, minerals, biochar, so they are all not independent so much, but each one of them eventually puts more and more organic carbon in persistent form or inorganic carbon into the soil, and obviously some of it makes it into the groundwater, the rivers, and into the ocean eventually, where it gets sequestered. Why am I not moving here? Something got frozen. Uh-oh. That's not good. Okay. I don't know. Am I still recording? Yes, I'm still recording. 12 minutes? Really? Okay. That doesn't matter. So this is the EW, enhanced weathering for soil organic matter, enhanced weathering with biochar, soil organic matter and biochar. So CO2 emissions and removals associated with mineral-based carbon dioxide removal CDR methods applied to soils and their synergies. So addition of minerals to soil for enhanced weathering and soil organic matter have synergies. So over time you have tons of CO2 per hectare per year, emissions and removals. So we have emissions from soils, mining, grinding and spreading, and you have CDR in inorganic form and CDR in organic form and soam. So you have increasing and eventually topping out here. Maximum rock CO2 drawdown potential based on inorganic carbon and soil organic matter formation. With EW biochar, again very schematic, over time you can still have synergies, and there are various details here that I'm going to skip, but you get the idea how each one, as we talked here, has synergies. So these two and this one, they all have synergies for soil inorganic matter and organic matter, and over time both inorganic and soam can sequestered into the soils. Synergies between methods to enhance CDR then. Well, 3 soil-based CDR methods that use minerals, so enhanced weathering, biochar and soam accrual, have traditionally been viewed in isolation from one another. There's clear scope for synergies between them. That is, strategic deployments of mineral amendments have the potential to sequester carbon through more than one CDR method, i.e. by directly sequestering inorganic carbon through enhanced weathering, increasing the carbon sequestration efficiency of biochar, and by enhancing the capacity of soils to store organic carbon matter, so as MAOM and AgOM. So that's accumulation and aggregation, allowing for both inorganic and soam formation in soil, allowing for both inorganic carbon and soam formation in soil does not require any additional preparation, only rock mining, grinding and spreading. Obviously there is a life cycle analysis needed there in terms of the energy used, the other emissions, and so on and so forth. Yet any increase in CDR impact directly reduces the costs per CDR unit, which makes this an economically attractive strategy. The cost for producing minerals biochars can be higher than the cost for producing biochars not doped with minerals. However, doping can also reduce biochar CDR costs due to a lower requirement for biomass feedstock. What do you pyrolyze to produce biochar? That's the biomass feedstock. This is for producing amount of stable carbon, so the costs work out essentially when you seed them with minerals. Inorganic carbon and soam formation adds extra CDR on top of CDR associated with the carbon content within biochar. This section discusses how such synergies between CDR methods can be achieved, specifically examining optimal mineral type and environmental climate properties, which I'm going to skip. So just briefly, mineral stability for synergies between CDR methods. So it's a long section. I'm just reading the headline. In this section, we discuss a range of minerals in detail with respect to their suitability for mineral-based CDR approaches, including global availability and cost, which are prerequisites for large-scale application of mineral-based CDR. Table 1, which I'll shows a detailed evaluation of mineral suitability for the three main CDR methods discussed here, and Figure 3 summarizes the key results for different mineral classes, which I will show next. So again, not going to read all of them, but assessment of mineral, rock, and residue types regarding their suitability for enhanced inorganic, soil organic, and biochar carbon formation. So mineral types in detail: primary silicates, wollastonite, I see here, pyroxene, micas, alkali, feldspar, quartz, and so on. In primary silicate containing rocks, you have basalt. Secondary phyllosilicates, you have illite, smectite. You can say I'm not a geologist or a chemist. Vermiculite and kaolinite. So these are the various contents. Weathering rates very, qualitatively very high. Some have low, some have medium, and so on. Enhancing capacity, very low for most of them. High here for secondary phyllosilicates, and medium for some. So predicted potential for enhancing CDR, again qualitatively, for inorganic carbon, mostly high, medium, and for facilitating soil organic matter, a lot of mediums and a couple of lows, and biochar carbon, a lot of mediums and some low, but some highs here. So, obviously there's some optimization needed, and there are others here like ordered Fe and aluminum oxides, short-range ordered aluminosilicates, non-silicates, and residues, and so on. So you can go through the details if you wish, but obviously it's all kind of qualitative at this point in terms of their ability to enhance CDR. So here, potential of mineral classes to result in carbon dioxide removal synergies. You are talking about enhanced weathering, biochar, and soam that we talked about. So this gives you an idea of how to optimize them. Primary silicates here, non-silicates and residues here, short-range ordered aluminosilicates, ordered iron and aluminum oxides, and secondary phyllosilicates here. So there is a way to optimize these things according to them. To conclude, here we reviewed 3 soil-based CDR methods that use minerals, including enhanced rock weathering for organic carbon formation, secondly mineral doping of biochar for biomass carbon retention, and thirdly accrual of soil organic matter. We highlighted their potential use and limitations when applied individually for CDR. We then assessed the potential for synergies between inorganic carbon, soil organic carbon, and stable biochar carbon formation through strategic applications of primary and secondary minerals to soils, or as additive to biomass, so biomass doping as they call it, before biochar production itself. We described the suitability of a variety of minerals for these synergistic approaches and highlight how carbon can be drawn down simultaneously through multiple soil-based CDRs. We suggest that such synergies can reduce the economic costs of atmospheric CDR by concurrent drawdown into organic carbon and inorganic carbon forms. The minerals with most potential for further investigation include primary minerals for SOM EW synergies, silicosilicates for SOM biochar synergies, and combustion ashes for synergies across all of these CDR methods. Further research is urgently needed into optimizing mineral formation through co-application of several minerals, i.e. primary and secondary minerals, to accelerate carbon drawdown through several pathways. Optimization of synergies between CDR methods could boost CDR rates and increase economic feasibility and hence favor large-scale rollout of land-based carbon sequestration. Of course, there are potential externalities like enhanced soil carbon leading to enhanced vegetation biomass and of course crop yields and farmers' incomes and so on, and it could be a virtuous cycle. So good ideas obviously need to be tested, and life cycle analysis, scalability and so on. Okay, let's leave it here.